Okay, we're looking at Relations Galore worksheet. It's the second worksheet, note sheet in your package, and it is basically extending further into different types of relations, not just linear. We've talked about domain and range already and types of ways of representing relations, and so we're just looking at a few different types. So just a reminder, a relation is used to describe the connection between two variables as independent variable and a dependent variable. A relation can be represented with a set of ordered pairs where the first elements of the ordered pairs are values of the independent variable. Second elements of the ordered pair are corresponding values of the dependent variable. In other words, a relation can be defined as a set of ordered pairs. The domain of relation is a set of all the first elements. Range is a set of second elements in the ordered pair. If there's no application to the particular relation, then often we're using X values for domain and Y values for range. And so your chart would be an X, Y table of values. But if there's a application that we're dealing with, then it's not just X and Y. So in the last notes, we represented it as a set of ordered pairs, table of values, arrow diagram, a graph, an equation, and words. Okay, and we're going to do this, some of the same in this. Okay, so here's another example, the sum of consecutive odd numbers. So if you calculate the sum of consecutive odd numbers, an interesting pattern arises. So first thing, you need to remember what consecutive. So that means in order. So if we're talking about consecutive integers, then an example would be 3, 4, 5, or -2, -1, 0. They are in order by adding 1 each time because integers go up by 1. If we're talking about odd numbers, consecutive odd would be, well, the first odd number, positive, is 1, then the next odd is 3, then 5, then 7, then 9, etc. So if we're taking the sum of consecutive odd numbers, that's what we're adding together. So in our chart here, it says the number of consecutive odd numbers. These aren't odd, right? 2, 4, 6 aren't odd. This is how many. So if we take one consecutive odd number, that's just 1. And the sum of all of those is just 1. But if we have the first 2 consecutive odd numbers, that's 1 plus 3, and 1 plus 3 is 4. So you can see there's 1 here, there's 2 here, there's 3, there's 4. So that's the number of odd numbers, not the actual value of them. Then if we add these 3 consecutive, that is 9, 4 consecutive. So basically, it's the previous plus the next consecutive odd, so that's 16. Okay, and then we need to complete the table. So that would be 1 plus 3 plus 5 plus 7 plus 9. So we add 9 to this, which is 25. And then 1 plus 3 plus 5 plus 7 plus 9 plus 11, and that gives you 36. So hopefully you see a pattern in that last column. So examine the sum values, what's special about them. So these numbers, 1, 4, 9, 16, 25, 36, hopefully you remember back, I think it's Math 8, where you start learning about perfect squares. Okay, those are all perfect squares. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. The pattern can be continued. If the first 15 consecutive odd numbers are added, then the sum is, well, that's going to be, take a look. So this is 6 squared, and that was for 6 consecutive odd numbers added together. So this would be 15 squared, which is 225. Okay, how many consecutive odd numbers were added if the sum is 1024? So now you want to think about what squared equals 1024. So remember, you've learned a little bit about square roots, so you can take the square root of 1024. If you're not sure, I just have to get my calculator up here. It's not something that you might know off by heart. Hopefully, once we do roots and powers, you probably will. But we'll go square root 1024. Okay, so that's 32. 32 odd numbers. Okay. Represent the relation with an equation that relates the sum s to the number of consecutive odd numbers. So the sum will equal, that's a capital S, consecutive odd numbers squared. That's your equation. Notice how it's not linear. Linear has just, that would have just the variable n, nothing raised to an exponent. Represent the relation between the number of consecutive odd numbers and their sum with words. Well, before we did this with words first. So the sum of n consecutive numbers is the square of the number consecutive numbers. Square of means you're taking the number of consecutive numbers and squaring it. Okay. Represent the relation between the number of consecutive odd numbers and their sum with an arrow diagram. So that, remember, you need two kind of oval shapes. Not there. And you put them in order. Okay, so we went in our chart. What did we go up to? We went up to 6, I think. Yeah. Okay. So we'll go 1, 2, 3, 4, 5, 6. And then we had 1, 4, 9, 16, 25, 36. And then just arrows that match them up. Okay, in this case, both the domain and range are in order, so the arrows will be horizontal like that. And this will be the number of consecutive, and this will be the sum. Domain and range, so domain. So in this case, this is going from 1 to 6. Now we could really do this forever. So in this case, we're going to do this for all sums, okay, and all consecutive numbers. So in this case, I'm just going to start 1, 2, 3, and then put dot, dot, dot at the end, which means it follows that pattern to infinity. The range, this would be 1, 4, 9. I'm going to do maybe one more so you can see the pattern, and dot, dot, dot to infinity. Okay. Yeah, is this data discrete or continuous? It's discrete. Oops, I always put an E there. It's discrete because you can't have a sum of 2.5 odd numbers, right? It has to be a natural number value of odd numbers, and that will result in a natural number answer. So you can't take the sum Represent the relation with a graph, scale, and label the axes. Use the arrow, the answer from the previous question to decide whether or not to connect the points. So notice how no scale is given. We really only went up to 6 for n. You can keep on going, and then 36. So here, maybe because it's such a big scale, you might want to go up by every 2 grids by 1. So every second one be labeled, and you can keep on going. Remember, this is the number of consecutive odd numbers. Okay, and then we just need to get up to 36. So I always count the grids here: 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 20, 22-ish. So if we, I'm going to go up, every grid is 2 units, right? There's not enough to go by ones. So that'll be 2, 4. If your writing's big, you could even skip so that you know the next one's 6, so the next is 8, 10, 12, 14, 16, 18, 20. So it just depends on your how big your writing is, your pencil. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. I'm going to stop there because I know it's the last one for our table of values. This, for me, is a little bit hard to write on the side. This is the sum of consecutive odd numbers. All right, that wasn't so bad after all. Okay, so so for one consecutive odd number, that's just 1. For 2, that was 4. For 3, that was 9. 4 was 16. 5 was 25. 6 was 36. Where is it? There we go. Okay. Just make sure those are lined up. And so remember, it says think about whether we join them up. So we don't join them because they're discrete. You'll notice that they don't form a straight line. If you try to get a ruler and make a straight line, that doesn't work. And that's because you're squaring the n value, and that is not a linear relation. Okay. And then speed versus time. So Sam needs to travel 120K. He can travel the distance using a variety of speeds. As Sam's speeds increases, the travel time, the time to travel 100K. Well, think about it. The faster you go, then the faster you will get to wherever you're going, so the less time it will take. So the time will decrease. Oops, so decreases. So complete the following table, round answers to the nearest hundredth where necessary. So you really remember distance equals speed times time. So you're solving for time, so that's distance divided by speed. And distance is always 120 divided by your speed. So 120 divided by 20. Okay, that's 6 hours. 120 divided by 40. Is 3 hours. 120 divided by 60 is 2 hours. So you can see it decreasing as his speed is increasing. 120 divided by 80. So that we can use decimals. So that's going to be 1.5. Okay, then 120 divided by 100 is 1.2. 120 divided by 120 is just 1 hour, obviously. and then 120 divided by 140. I'm not sure exactly what that is, so I'm going to use my calculator. 120 divided by 140 is 0.86 if we go to the nearest hundredth. Okay. So are the speeds listed in the above table the only speeds that Sam could travel? If not, what other values are possible? Well, no, Sam can travel at any speed. Now, saying that once you get to, this is getting dangerous after 140K, you get a ticket for some of these values. And also vehicles, there's a certain limit to some vehicles, how fast they will go. But really what this question is getting at is, could Sam travel at 70 kilometers per hour, or 102 kilometers per hour, or 105.3? So yes, Sam can travel at those in-between values. So these are not, no, Sam can travel at other values as well. So example, 72 kilometers per hour, or 95.5 kilometers per hour. Okay, it's just your speedometer on your vehicle won't give you, or is it odometer? In any case, it won't give you the speed as accurate as every, how many decimal places. But technically, it could be any decimal place between, in this case, 95 and 96. So what are the domain and range? We can't list all those values because there's an infinite number between each natural number. So we then write our domain. We know that our speed here, we'll call this S, right? And this T. So our domain is going to be S, and S can basically be anything greater than or equal to 0. Okay, now if it's equal to 0, then he's not going anywhere. So I'm going to keep it as greater than 0. When you're doing this kind of domain, when you're not listing it, you have to state what variable you're dealing with. So S inside your set brackets, and then you use a vertical line, which means such that, or where. So you're looking for all values of S where S is greater than 0. And then we put a comma, and S has to be an element. So it's a funny looking E, element of the set of real numbers. Okay, so you need this funny, it's a Greek E. I'll do it again a little bit better. So it's kind of like a C with a line in it to make it an E. Real numbers is R. I do 2 bars to mean the set of real numbers. In textbooks, sometimes you'll see it bolded. Okay, but that just means you'll have every decimal value. Okay, fraction or decimal that's greater than 0. Now, as I said, technically there's a limit to your vehicle and speed limits and all that kind of thing, but ideally S could be greater than 0 to infinity. Okay, your range in this case is T, so all values of T where, and in this case, what's happening here? Well, these are decreasing, right? So again, you can't go negative, can't have a negative time, that doesn't make sense. And so we have to think about time will never be negative, so it'll be greater than 0. And is there an upper limit? Well, let's say your speed was 1. Then it would be 120 over 1, so it would be much bigger than this. If your speed was 0.5 kilometers, it would be, time would be 240 hours, etc. So it really goes to infinity. Again, are you going to travel in a car 0.2 kilometers per hour? No, but in terms of the availability to do it, you could. Okay, so this will be t greater than 0 as well. And then t is an element of the set of real numbers, and close your brackets. Okay, so that is called set builder notation. So this is called set builder notation for domain and range. Because we'll learn Math 30, you'll learn another way of showing domain and range. Okay, represent the relation with an equation that relates the time t to the speed s. Well, we actually already did that, right? Up here. So t equals 120 over s. So t equals 120 over s. Determine the time when the speed is 25 kilometers per hour. So that means you just put in 25 here. So quickly, 120 divided by 25 is 4.8 kilometers per hour. And then determine the speed if the time is 5 hours. So I'm just going to copy this out again. It's not right above, and I'll put 5 hours and then 120 over s. You always just want to make sure that your units are jive, basically. If this is kilometers per hour, you're given hours, all good. If you were given this in minutes, then when you're finding your speed, it will be kilometers per minute. So just be aware of that. So when we solve this, we want to multiply through by s, both sides. So the s's divide out, and then we get 5s equals 120. And then we want to divide by 5. Try to make your 5s look different from your s's. And so those will divide out. So s equals 120 divided by 5, which is, what is that? 24. And that will be your determine the speed, so kilometers per hour. And I just realized I made a mistake here in the units back up in the previous one. This should be hours. Okay, determine the time, and this was speed. Okay, so go back and change that in question 15. And that's, oh yeah, I forgot we have to graph it too. So is this data discrete or continuous? Well, as we talked about, you can have a decimal value of the speed. So this is continuous. You can drive at a decimal value, decimal or fraction value of kilometer per hour. Okay, so now we have to think about the graph. And so now when we take a look at our table of values, our speeds were, we went from 20 to 140, and the speed was our dependent. So over here, I'm going to go to the bottom. Just want to make this what? Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we don't have enough to go like every 5 or whatever. We could go every 10. So this would be 10, 20, and then again, if your writing's big, go every second one would be 40, and then 20, 40, 60, 80, 100, 120. Because if we went 5, we would run out of space. We wouldn't get to 120. Okay, so this is your speed, and that's in kilometers per hour. Then our distances, or sorry, our times for 20 was 6, basically down to 0. So we can make this, there's a lot of space here, right? So maybe, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21-ish. So we could go every 3. So this would be 1 here, 2, 3, 4, 5, 6. Okay, so when we're traveling, oh, and this is time in hours. And so for 20 kilometers per hour, it would take 6 hours. And 40, remember it took 3 hours. 60 was 2. 80 was 1.5. Oops, 1.5 needs to be up a little bit. 100 is 1.2. 120 is 1. 140 was 0.8. So this is 6. So 140, didn't put that in, be here. Okay, and so you can see it's curved. And in this case, we do join it. And so this is going to be a little bit harder for me using my freehand on this. Okay, got a little wonky there, so kind of goes like that. Okay, and this goes up like this. So we put arrows on the end when we join it up, and basically here, this horizontal axis, it will never touch it. It'll approach it but never touch as time gets, as the speed gets bigger. So we call that an asymptote. We'll talk more about that. And then here, this will never meet the vertical axis. It'll get close but never touch it. Okay. And then we're done.